Hello everyone, it's me, Billy Younger. This time I'm here to solve another oscillation example. This is Oscillations Example 5, and in this case I'm actually going to discuss all the or not all of them, but I'm going to discuss a lot of different systems that physically behave like the simple harmonic oscillator we've been studying, and I'm going to try to explain how you can see that in one case. It's basically just by trial and error. You can look at the individual data points that you get from a function and see that they match exactly the x equals a cosine omega t plus phi function. In other cases, we're going to actually work it from the differential equation, i.e. the equations of motion. So let's go ahead and get started by sharing my iPad screen with everyone. I have written this as if it were a problem, and I've written the problem to say, list and explain how a few other physical phenomena can be faithfully represented by the SHO or SHM simple harmonic motion equation and or its solution x equals a cosine omega t plus phi. So I often use SHO. I used to use nothing but the phrase SHM, but now I've sort of migrated to SHO. But I do know a lot of literature still uses and textbooks still uses the SHM. So that's why I just wanted to point out that you might run into people calling it simple harmonic motion as opposed to simple harmonic oscillations. They both mean the same thing, though. So, first off, I wanted to explain that the one physical phenomena that behaves just like the simple harmonic motion is specifically anytime an object travels in a circle at a constant speed. So if you just imagine an object going at a constant speed in a circle of some radius, what you can figure out is that that is actually matched. Its x coordinate specifically can be written as a cosine omega t plus phi. Similarly, its y can also be written as a cosine omega t plus phi. The only difference is the x and the y are obviously at different phases because, as you can imagine, if you imagine the x-axis being left and right and the y-axis being up and down, when the particle is at the maximum x, it'll actually have a value of y equal to 0. And then when the particle has a 0 value for x, it will have a maximum value for y or a minimum value for y. Similarly, when a particle has the minimum value for x, i.e. negative r, then the y would have a position 0 again. So this is most easily seen by just testing it. So what I will tell you is there's a wonderful vector expression, and here's the vector expression. I'm going to write out solution again like I always do, even though this one isn't so much of a solution type thing. But what I'm going to say is try plotting the points xi comma yi for t equals 0 t over 8 t over 4 3t over 8 t over 2. And we could keep going in eighths, or we could just go to quarters if you want to, but I'll try to continue going on in eighths. So we'll actually move up to 5t over 8. And then, of course, 6t over 8 is 3t over 4. And then we could say 7t over 8 and just plain t. And specifically, this is for the vector function r equals, what I'm going to do is write the x component as r cosine. I'm going to put the 2 pi. Remember, we normally say omega is 2 pi f or omega is 2 pi over t. I'm going to write the 2 pi and I'm going to write it 2 pi over the period so that we'd see t is the period we're talking about. So omega t becomes 2 pi t over the period capital T plus phi, and that's in the I hat direction. Plus we also have R sine, again the same argument, 2 pi time divided by the period plus phi, and that's in the J hat direction. So if you actually take the time and make a table of x comma y values, you'd actually have to make a table of like t and then x and then y, and then you use all those t's that I just expressed, and that would give you the actual coordinates. And when you plotted those coordinates, what you'd see is that t equals 0, the particle starts at specifically some angle phi, more or less, but you could assume the phi is equal to 0. Now, in that case, you would actually get circular motion. You could figure out that the velocity is going to be just 2 pi over t times the radius. You could find that the acceleration is going to be 2 pi over t times 2 pi over and when I'm saying 2 pi over t, I mean 2 pi over the period times 2 pi over the period times r again, and you would see that it is actually circular motion. You can see the y is also that just by realizing that, remember, sine and cosine are sine and cosine specifically because sine is the ratio of the opposite side to the hypotenuse for a given angle theta, whereas cosine is the sine of the complementary angle to the angle theta. In other words, they just differ by an angle of pi over 2, so you could actually call cosine pi over 2 minus theta is exactly the same thing as sine of theta. So because of that, you can see that the r sine 2 pi t over t lowercase t over t plus phi is also a simple harmonic motion equation, just shifted by a little bit. So that's one of the particular instances. And because of that, you can see that omega, which would normally be the thing that goes under the square root, is just the 2 pi over the period. And of course, you know that frequency is 1 over the period and stuff of that sort. So you could actually use all this and just describe the motion. Now, you don't necessarily have to revert back to the differential equation in this. This just happens to be a particular physical phenomena in which the solution of the simple harmonic oscillator equation fits the motion in the x direction, but it also fits the motion in the y direction as a simple harmonic motion. So if that doesn't convince you by just filling out this table and seeing that it makes exactly the kind of circle that I expect that you expect, then you can also see a specific link on YouTube that's pretty nice, and that's basically just https colon slash slash YouTube. Notice I wrote YouTube a little differently. I'm actually writing exactly what I copied from the YouTube link. So it went utu.be. Then there's a capital J, a capital S, a capital B, a lowercase w, a minus symbol, a capital J, a lowercase y, a capital F, lowercase g, capital Z, lowercase k, question mark, lowercase s, lowercase I, equal symbol, capital M, capital G, 5, minus, capital Y, number 3, capital V, capital I, capital Z, capital D as in dog, 9, capital L, lowercase k, and then 2, 3, capital T. So that link will also give you a nice video that explains to you not only how the X position, remember in XY coordinates, the X coordinate is called the abscissa, and then the Y part of that's called the ordinate. So you could just say the ordinate and the abscissa separately are each obey that, and that video shows both of those as well as it shows a pendulum. But anyway, that's one particular solution or one particular physical phenomena that can use the simple harmonic oscillator or simple harmonic motion as the solution to describe the actual motion. There's also another one, specifically a pendulum. So, for instance, if you imagine a ceiling and then have hanging from it a simple pendulum, which is basically a massless string that's free to oscillate back and forth. And we'd say that angle right there is theta. And if we use that theta as the actual coordinate, we can derive a equation of motion from Newton's second law, specifically Newton's second law for rotation. We can derive an equation for motion that you'll see is equivalent to the simple harmonic oscillator equation, as long as we make one little assumption, and I'll go about that. So what we have here is a ball whose mass is much greater than the string that's holding it to the ceiling. And in fact, we're going to say that the distance, oops, there it goes, converting to an eraser again. We're going to say that the distance from the center of the ball to the center of rotation of the pendulum is a distance L. We're going to say the ball has a mass M, and therefore it has acting on it a force mg, and that can be broken up into a force that is parallel to the string and a force that is perpendicular to the string. And this one, of course, the one perpendicular, excuse me, the one parallel to the string, given this angle theta is the same angle as we saw up there, this one's going to be mg cosine theta, and this one's going to be mg sine theta. So now that we have that, we can use, instead of using Newton's second law, I'm going to use the Newton's second law for rotation, and that's going to give us that the summation of all the torques is equal to I times, we would normally just say alpha, but again, this time it's not a constant acceleration, so I'm going to have to use d2 theta over dt squared. And I'm only talking about rotation about one axis, so I didn't need to mark it as a vector. And in fact, the only force I have here is going to be, or the only torque I have here is going to be the torque associated with the mg sine theta. It's actually the torque associated with the mg, but only the component perpendicular to the lever arm matters. So I can compute the torque to be L times mg sine theta, and it's a restorative force, so I'm going to put a negative on it because as you can see, when theta gets larger, the force is actually pointing in the opposite direction to try to reduce it. So it is that restorative force. And then the other side is I, the moment of inertia, but for a mass on the end of a string, basically the entire mass is out of distance L, so the moment of inertia for that particular thing is ml squared, and then we have theta double dot. Remember, theta dot means the derivative of theta with respect to t. Theta double dot means the second derivative of theta with respect to t. So now we almost have what we're shooting for. I can see already that I can divide through by L, and that'll get rid of the L on the left and the exponent on the right. I can also divide through by M, and that will get rid of the M. But when I try to write the equation like the simple harmonic oscillator equation by putting everything on one side and zero on the other, there's a little problem. Specifically, I'm going to have L times theta double dot plus G times sine theta is equal to zero. That is not the same as the simple harmonic oscillator. The simple harmonic oscillator has to have the function times a constant. And I actually have the function theta in this case. I have the sine being taken of it. Uh, First, I'm going to go ahead and divide through by or multiply through by 1 over L. So I'm going to do that to both sides, and I'll just write it as if I'm doing it all the way across like this. Of course, the right-hand side's not going to change because multiplying 0 by 1 over L still gives you 0. But now I have theta double dot plus G over L sine theta is equal to 0. Now, if we use a Maclaurin series expansion and work out what sine theta is, if you expand it, like I said, a Maclaurin series, so you're expanding about x equals 0 or about theta equals 0, what you'll find out is that you get 1 over 1 factorial x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth power minus 1 over 7 factorial x to the seventh power plus dot dot dot. Now, that's an exercise that I highly recommend you guys do at some point. Not only you do the sine theta, but you do the cosine theta and you do e to the I theta as well, so you can learn Euler's formula as well. But it's just good practice. But the main thing that we see here is if we choose particularly small values of theta, then the very first term in sine theta is approximately just theta. Okay. Stupid me, I wrote it as X, which was completely erroneous, but let me fix that real quick. But that's basically what we're trying to see here is that if we did a Taylor series expansion, or in this case a Maclaurin series expansion, then the sine of theta is approximately equal to theta. But if you want more terms, then it's minus 1 over 3 factorial theta cubed plus 1 over 5 factorial theta to the fifth minus 1 over 7 factorial theta to the seventh. So I apologize for writing the x's there, but that's basically what the sine is. And therefore, for small theta, sine theta, I should have wrote that sine theta is approximately equal just to just theta because 1 over 1 factorial is just 1, so it's just 1 times theta. So if we make that assumption, and by the way, it's not as limiting as you might think. For instance, you can get like up to around 20 degrees before you get a whole 2% error. So it's not that huge of a indicator or a huge of a limitation. So we can work with that. That being said, I'm now going to replace the sine theta with theta, and the equation of motion, the differential equation, becomes theta double dot plus g over L times theta is equal to 0, which is exactly the form of the simple harmonic oscillator. And remember, the simple harmonic oscillator gives us a solution x of t, or in this case it'd be theta of t, gives us a solution theta of t is equal to some amplitude, which you might call A, or you might call theta 0, or theta sub A, or whatever, times the sine of, remember we take the square root of whatever is being multiplied by the zeroth derivative of the function, which in this case, the zeroth derivative of the function is just the theta of t, and what's being multiplied by it is g over L. So I'm going to write it in as the square root of g over L times theta plus phi. So again, you could have written this as a times the sine of the square root of g over L times theta plus phi. That would be fine as well. But the main thing is you see yet another solution or another physical phenomena that has a simple harmonic oscillator as a solution. So I'll go ahead and box this off, and that's for the simple pendulum. Now, there's also one for a more complex pendulum, specifically the physical pendulum. So if we want to address that, we can look again and just imagine a ceiling, and we'll have some kind of connection. Actually, a ceiling is probably not a best thing to draw for a physical pendulum. What I'm going to do instead is I'm going to imagine that a physical object, I'm going to draw it sort of like it looks like a bat or a chicken leg or something like that. Okay. And what we're going to imagine is that there is a pivot point right here. So we'd have some kind of, for instance, a hole drilled through the chicken leg or baseball bat looking thing, and a nail could stab through there and be fairly frictionless by maybe putting some bearings in it, and then you could just tilt the physical object. But what we know is when we have a physical object that's not a point particle or is not a massless string with a point particle on the end, we know that the laws of physics tells us that gravity and other forces act as if they're acting at the center of mass. So if I drew down here the capital C, capital M, then that means the force of gravity is actually going to be acting right here, and its mass M suggests that the weight would be mg. So we again get another torque type problem, and we could imagine, for instance, this as the angle theta, and we would say this length from the center of mass to the pivot point, we could call that just equal to something simple like L or R or something along those lines. And I'm actually trying to remember what your book used for that. Oh, your book used H, so I'll go ahead and put a H there. So if we call the distance from the pivot point to the center of mass H, then that's the actual length of the lever arm. And just like we did before, we'll make a component of the weight that is parallel to the string, and then we'll make another component of the weight that's perpendicular to the string. This one will be mg sine theta. Of course, it's in the negative direction, just like we had before, so it's still a restorative force. And this one be mg cosine theta. Now, with that in mind, we can go ahead and take the summation of the torques is equal to I times, I'm going to call it theta double dot, just because we did alpha before and I showed you that that should be theta double dot since the alpha is not going to be a constant. And again, we only have one axis of rotation, so we don't need the vectorness of it. So what I'm going to do is assume the actual object has a moment of inertia I. So I'll just do a capital I. And with that in mind, I will have H times negative mg sine theta is equal to I, which I'm just going to call I, times theta double dot. Again, if we assume theta small, then sine theta is approximately equal to theta, and we can get I theta double dot plus H times M times G times theta is equal to 0. We divide both sides by I, and we're going to find that theta double dot plus M times G times H over I times theta is equal to 0. So we see that theta is equal to A sine square root MGH over I times T plus phi. In other words, the omega, as we always advertised, is the square root of whatever the coefficient is in front of the theta function or x function or whatever the non-differentiated function is. So that is the simple harmonic oscillator solution for a physical pendulum. So we've got that. And I have one more specific example I'd like to expose you to, and that is called the torsion pendulum. So the torsion pendulum actually shouldn't be there. Hold on a second. So we're now going to go ahead and talk about the torsion pendulum. So here's the torsion pendulum. SION. I don't know why I spelled it backwards like that. It turns out for a torsion pendulum, we have a Hooke's law type scenario that basically says the torque twisting some kind of ribbon that is used to make a torsion pendulum is actually directly proportional to and restorative so that it's some kappa times theta, meaning the actual force is just like F equals negative kx, but in this case, it's torque equals k times theta. So, what do we mean by a torsion pendulum? Well, what you can imagine is a little flat ribbon, and if it's round, you sort of don't get the feel that twisting it's going to cause it to do anything. But if you think about it flat, it feels a little more natural to actually be associated with a specific twistingness or orientation. So what we can imagine here is this object. I don't know why I'm drawing it in red, but it's good enough, I guess. This object goes something like this. That didn't turn out as nicely as I'd like, but anyways, that's good enough. And with that, we can say that that particular object has a specific moment of inertia I. And there I go erasing again by accident. So this will be the actual body like this, and we're seeing through it by seeing this little bit. So what'll happen is as we twist this object, say this way, that's going to tend to rotate that little blue ribbon that we see here. That is actually up in front of this. So that's going to tend to twist that little blue ribbon, and when that little blue ribbon is twisted, that's going to make it want to try to twist back to its original position. And it turns out that that angle, when it's twisted through, that angle is theta, and the torsion or the torque supplied by that is negative k times theta. So using torque is equal to I times theta double dot, summation of the torques is equal to I times theta double dot. We only have one force on it. It's negative kappa theta is equal to I times theta double dot, which we can represent as theta double dot plus kappa over I theta is equal to 0. So again, we have theta of t is going to be some a times cosine of omega t plus phi, where in this case, omega is going to be the square root of kappa over I. So again, we can get all the stuff we had before, but we now can do it instead of just for a simple mass on a spring horizontally. We could also do it for a physical pendulum, a simple pendulum, a torsion pendulum. You can also do it, by the way, for a pendulum, or excuse me, for a mass on a spring that's hanging vertically. In that case, you just take the equilibrium position as sort of your coordinate origin, and that equilibrium has to occur as a result of the mass m being pulled down by a force mg. And when that comes to a stop, that's the equilibrium position of the spring, and then you use that as the coordinate of your the origin of your coordinate system. But this is the solution that we get when we're talking about the torsion pendulum. And I think that does a pretty good job of mentioning all the different ways or many different ways in which the simple harmonic oscillator, the simple harmonic motion, describes various physical phenomenon, or phenomena is the plural. And I hope you find that somewhat helpful and can now solve more physics problems. Have a nice day.